Good afternoon, ladies and gentlemen. If everybody can make their way in here. We're late. Are we late? Okay, today it's our pleasure to have Cathy Clerbaux who's going to speak to us. Cathy's been visiting ACD for the last few months, working in my group, the ACREST group within ACD. She's been working on a lot of things, but especially looking at some comparisons between the IASI instrument and its measurements of carbon monoxide and those of MetOp-A. Cathy is a Directeur de Research, first class, and as a senior scientist at CNRS. She works physically at the LATMOS IPSL facility located at the Université of Pierre and Marie Curie in Paris. She's also a visiting professor at the Université Université Libre de Brussels, and also a regular visitor with us in NCAR every year. Cathy's background is a spectroscopist, and she got her PhD from ULB and is now internationally recognized as an expert in atmospheric composition remote sensing, involved in a number of different science teams for instrumentation looking at pollution in the atmosphere. And in particular, as I mentioned, Cathy has been working on the IASI instrument, which IASI has a number of copies which fly on the EUMETSAT series of satellites, the EUMETSAT MetOp series of satellites. And the IASI has been providing us with many exciting examples of air quality and climate relevant trace gas observations. Cathy is at the moment PI for the IASI next generation instrument and involved in the planning for pretty much all of the European follow-on missions for atmospheric composition. And today she's going to give us an update on the IASI mission, particularly observations of local pollution events, and I'm sure she'll talk about some future plans. So welcome, Cathy.
Thank you very much, David. So thank you all of you for being here. And in this talk, I'll try to give you some example of the things we have obtained regarding to the IASI mission this year. So it will be all new what you will see. Some of the things we have, it's the first time that I'm showing them. So most of the results I'll show are coming from students, either PhD students, either postdoc coming from LATMOS or ULB team. I work at both locations, as David just mentioned. So before starting to show you some example, I'd like to give you some background on how it was to define this mission and how long it took, in fact, to have this mission settled up. And at the very end of my talk, I'll give you some highlights on what's going to be next. So this is in French, but I was glad to find this document because, in fact, it was written in 89, which is pretty long ago. It was basically when I started to do my PhD, so that's a while ago. And in this document, you see that for the future, we had defined the need for an atmospheric chemistry mission. It was called at that time GlobeSat. Never exists this GlobeSat satellite, but interestingly, you will see that the payload that we defined at that time contained a lot of different instruments that basically made their way through one way or another to different other platforms. So this is the ancestor of IASI. So we said, okay, we would like to have temperature profile, water vapor, some properties, relative properties, and also some integrated contents for some interesting species. And as you can see, there's a long delay between this date and when IASI was launched, in fact. And you can say the same thing for the other instrument. That's the ancestor of GOMOS. That's the one that flew on the megatropic satellite now called Scarabi. And this is also already the Polder aerosol sonder that it was defined here. So as you see, there's a very long delay between what we say we would like to have and when the satellite is, in fact, flying and providing data. So how do we define the satellite mission? So, for example, for IASI, we said, okay, we would like to measure something about the tropospheric composition. And we would like to use, in fact, the radiation that is provided in a natural way by either the sun in the UV visible, and that can be either reflected or diffused by the Earth's atmosphere, either with thermal infrared. So we decided it would be a thermal infrared instrument. And so what would you like to see? Of course, we would like to see and measure all the main, the primary gases, but they are present in the atmosphere with very large concentrations. So in the infrared, they will also bother you because it's, in fact, absorbing in a large spectral range, in particular water vapor. If you want to have access to other species, you will see that you have water vapor absorbing everywhere in the thermal infrared spectra, in fact. And so if you want to measure, for example, tropospheric ozone, you will also have the signature. When you record the radiance coming from the Earth at the 800 kilometers, you will also see the ozone coming from the ozone layer in the stratosphere. And you will also like to have access to a lot of other gases that are very important in tropospheric chemistry, like ammonia, for example, or the COVs, or a lot of the species that are involved, in fact, in the pollution events. So basically, you try to define a mission that, to some extent, can provide information on some of these species. There are, of course, other ways to have better measurements, more closer to the ground. You can also use aircraft data or balloon-borne data, but here I'll focus only on what the satellite can provide. So how do we define this satellite mission, in fact? We have first to start with the mission specification, which part of the atmosphere, which species, what accuracy, what horizontal coverage would you like, what we call the pixel size, which is the field of view that you will have, how well you will see the ground, how often would you like to have these measurements. And as soon as you agree on that, you have to design an instrument, and that will also cover which spectral range do you want to investigate, at what spectral resolution, what signal to noise. Then you have to define on which satellite would like to launch it so that it's using like a polar orbit or something different. And for that, we interact, in fact, a lot with the industry and also with the spatial agencies. These are, of course, very important because they will pay for the mission at one point. And for that, we also rely on the heritage, which is also very important because we can build on what we already know. And then the biggest step is to look for flying opportunities. There are some people in the room who know that very well. Okay, so in 1993, so that's when my postdoc started, it was already on IASI. And at that time, if you would have told me that 20 years after I will still be working full-time on IASI, I would never believe you. But okay, in 1993, that's basically what we defined for the IASI instrument, that we would like to have a Fourier transform spectrometer looking towards the ground with some ability to scan across track. And this is done, in fact, we see 4 pixels at the same time, and then it's moving in a perpendicular way to the track, and it's covering about 2,000 kilometers here. And it would cover from something like 650 centimeters minus 1 towards 2,700 centimeters minus 1, with a pretty good spectral resolution. For those who know TESS, it's a little bit coarser than TESS, but it's better than ERS. And it has also a good signal to noise, in fact. So at that time, in fact, it was very clear that the first goal of the mission was not atmospheric chemistry. And this is because it's EUMETSAT saying that. It's like for you, NOAA. And so that puts a strong constraint on the mission, is that the first priority is meteorology. Okay, so atmospheric chemistry comes second. It has, in fact, large implication on the next step. Because, in fact, EUMETSAT never really cared about delivering good atmospheric chemistry products, for example. Okay, so a little bit further, as you know, after we had to write a science plan when the mission started to be on phase A. So, by the way, the logo at that time was pretty awful. I never noticed that. So this is also from, I did some scan of very old documents, and that's seeing that now it's very funny, some sentences that maybe some of them I even wrote by myself, but you see that as the emphasis is really on meteorology. you see there's some sentence like information on other less abundant chemical species is also potentially available in the infrared spectra. And so we are very careful. We don't promise too much because it's not really the priority of the mission. But you can see sentence like the possibility, retrieve and IASI, blah, 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 and somewhere after, okay. Special geophysical events like volcanic eruptions, strong pollution, and then might be measurable, whatever. That's very interesting because IASI is very well known for that now. So that's very interesting to see that further away. Okay, so in 2006, so see the gap between, so it was very long to wait, and that gave me some opportunity to come here and work with the MetOp people because I couldn't wait for so long. And so in 2006, the first IASI was launched on the MetOp-A platform. So it's on a polar orbit. The local crossing time is 9:30 in the morning, and so the same in the evening. And so basically, one IASI observation looked like this. So this is a radiant spectra that was divided by the black body of the Earth, and it is composed of more than 8,000 of channels. It represents about 15 gigabytes per day, and we have a bit less than 1.3 million of these kind of observations per day. So that's huge. That's huge. And if I would have known, I would say that during the 10 years I've been waiting for this instrument, I spent a lot of time on developing a very nice retrieval algorithm. And if I would have known and do the things backwards, no, I would spend more time on trying to handle so much data because that's so huge and you have specific problem. You have to really to sort the data and to keep the more relevant one and to process the thing in near real time. And we never realized that at that time. I should also point out on the fact that among this data, there are half of it you basically throw away directly because they are cloud contaminated and we don't see through the clouds. But that still does a lot of data. And now, guess what? We have twice more data because we have 2 IASIs. So we really have like more than 1 million of data that we can use per day. So these instruments are so useful, in fact, for meteorology that the first instrument is was supposed to last for 5 years, so it has exceeded his lifetime. But they don't want him to die before the second one was launched, so they launched the 2 of them. And so the 2 of them are working, and for at least 2 years, we will have the 2 of them working. So this guy was launched in last September, 1 year ago. So those are some examples of what we can retrieve for IASI. So the 2 more mature products that we have for atmospheric chemistry are CO and ozone. I think CO came first, in fact, because we had the experience to work with the MetOp data. That really helped, in fact. So ammonia is also great. I'll show you some results on what we have on ammonia. I'm not going to talk about this guy. We do great stuff also to follow volcanic eruption, plumes following volcanic eruption. This is a CO movie. It's something, so like 20 years before, now we only saw that coming from models. Now we can do it directly from the satellite data. This is CO at the surface, and what you see is that you see a lot of pollutant escaping, in fact, from China, traveling around the globe. You see that the fire here, biomass burning fire, moving depending on the wet and dry seasons, and you see some hotspots at different parts of the globe. You can also have large fires occurring sometimes in the boreal areas. I think you know this kind of picture from the MetOp experience also. And so that's what I think now is that I think basically IASI is very useful for meteorology too because it's now, they say it's the single instrument that brought the more increase to the skills for the last few years. It's also, I think, on the same level, also very important for atmospheric composition measurements. And that's even more true now that you have all the US instruments that are maturing or even not working anymore. So I think we made we did some nice stuff for atmospheric chemistry. I think it's still under use for climate gas monitoring. It's still very tricky, in fact, to retrieve, for example, CO2 and methane with the accuracy that we would need to follow them and their change in the atmosphere. I think something that we did not anticipate is what we could get for the operational application, like fire detection or following volcanic plume. That's working very well too. And that's the list of species that we are able either to measure, either to detect. Not all of them all the time. Some of them most of them we only see in fires. Like for example, in pan, we only see pan in fires. So, and the one in black are the one that we, in fact, in the science plan that we listed as would be measurable by IASI. That's all the one we have now. Okay, so now I'll focus on some examples so that are very recent results. And before that, I'm going to show you how sensitive we are for the boundary layer. Because if we want to track pollution, in fact, we would like to see near the ground. So I'll give you some examples. But before that, you are all used of what an averaging kernel is. It's providing the sensitivity of your instrument towards the different level of the atmosphere. And as you know, thermal infrared instruments are known or generally considered as being very insensitive to the boundary layer. And this is because as it sees the thermal emission of the Earth, and sometimes the ground temperature is at the same temperature as the first layer of the atmosphere, or the temperature just above the surface, then you don't discriminate this first layer and the ground, in fact. But there are other situations of what we call the thermal contrast. In fact, it's the difference of temperature between the ground and its first layer. So if you look at the skin temperature during the day, during the night, that's an example for 1 month. It's I think it's May. And you look at the atmospheric temperature for the same month, you see that there are some differences. And if you look at what we call the thermal contrast, this difference, you see that sometimes you have a positive thermal contrast, which is provided, everything in red here is above 10 degrees positive, and everything in dark blue is minus 10 degrees in the negative. And when you have this thermal contrast, in fact, you can have some information even down to the ground. And that's what I'm going to show you. So basically, there are we put 3 cases, and there's a lot of cases in between. If you have exactly the same temperature at the surface and on the first layer, basically what you will see, in fact, here, that's the thermal emission of the ground that you have. It's a function of the emissivity and the temperature of the surface. And then when it's going through the atmosphere on the first layer, you have this emissivity, you have this emission, and it's somewhat absorbed by all the constituents absorbing in this first layer, and it's also re-emitted. And it's doing that on every layer that the radiation is crossing, in fact. But in the case where you would have these two that are exactly the same because the temperature is the same, then you have 0 here. But if you have a negative thermal contrast, then you will have the spectrum in emission because the temperature, in fact, of the first layer is higher than the temperature of the surface. On the contrary, if you have the temperature of the first layer, which is lower than the surface, you would have the spectra in absorption. And that's usually the case during the daytime, and that's often the case during the nighttime. But you can also have, you will see a mix of both during day or nighttime. So that's a simplified way to present it. So basically, no signature if you have the same temperature, or negative emission signature or positive signature. I'll show that on real spectra. So this is ammonia. The interesting thing about ammonia is that it has a short lifetime. It's not exceeding a day. And it means that it's emitted near the ground. And that's the fact that you see it from satellite. It's because of 2 things. It's because it's absorbing in a spectral range where basically nothing else absorbs. You have some water vapor lines, and so it's a very clean, it's in the atmospheric window, in fact. And the other reason, in fact, is because it has a clear spectra, and so you can, in fact, pick some lines and retrieve the ammonia signature. So here, what you would see, it's a the IASI spectra is in gray. As you can see, there's a lot of other absorber. That's ozone here coming. There are some lines of CO2. There are some lines of water vapor. And this is an absorption spectra of ammonia that you see the signature in the IASI spectra. And on the contrary, here, you have a different situation where you have the ammonia coming in emission. But what's very interesting is that the other species are still coming in absorption, because for ozone, for example, you will have the signature of ozone throughout the atmosphere. So that signature is coming from all the layers between the ground and, in fact, the stratosphere. Whereas for ammonia, you only see it near the surface. So you have the signature in emission, in fact. And so you can use that. Here, the situation would work, in fact, to retrieve ammonia. In fact, provided you do have some thermal contrast. If you don't have thermal contrast, then you have no signature. And that's a limitation, of course. So now we can draw some maps using that. So this is ammonia for daytime. That's an average for 1 month. And here, you have all the signature in emission. So red would be emission, so absorption, sorry, absorption. So you have all the signature in absorption because we are during the daytime, and the thermal contrast is positive. Here, we have some of the thermal contrast is negative. That's in this area, for example. Then you will have the spectra in emission. And for some in the fire region here, it's positive. So, but you can still interpret the signal. So you can do that and average that over several years and obtain very nice maps like we have here. This is an average over 5 years for the morning orbits, and this is for the afternoon orbits. And you can see that it's for it's for 1 year, and it's for 2010 because it's you see the Russian fire here, in fact. And if you have a closer look, we can see a lot of stuff. If you zoom on all this area where you see hotspots, in fact, of ammonia, you can really track that it's the hotspots are always occurring about where there is a lot of agriculture, for example, because they use ammonia as fertilizer. Okay, so the ammonia retrieval, I should say a word on that. It has evolved a lot since we started. It's only now, this year, that we are happy with the ammonia product. Just to, in very short, the first detection, we were able to do it because we saw a structure that we didn't identify that was occurring in fires. So after some digging, we realized it's ammonia, in fact. So we exploited this fact, and we averaged over 1 full year. And from there, we could retrieve, in fact, see that we can have some hotspots around the globe. But then we improved we in fact took better care of the fact that sometimes we don't see it. When the thermal contrast is weak, we don't see it. And so that was improved on that step. Then we use a proper, like we did for CO, we use a fast retrieval based on optimal estimation. And then we realized it was not working so well because people are so used, in fact, to use averaging kernels that they were surprised because the averaging kernels looks very weird for ammonia because it's always emitted only by the grounds. So it turns out that the modelers and so on, they couldn't handle that well, in fact. So we decided to do something else, and now we have another way to retrieve ammonia, which we call hyperspectral range index. I'll tell you a few words on that. That's where we are. And so this is the work of Martin Van Damme. He has a paper just submitted in ACPD about his work. So this is the spectral range where ammonia is absorbing. So this is the ozone band, and you have on the left wing and right wing, you have the absorption of ammonia. So what we used to use in the past, it was this only single line, which was very poor when we see that now. There was an English group by Walker et al. That did some nice retrieval, in fact, using a larger band. This is what we did with optimal estimation. And now we have a full band, and that's providing, in fact, much more nice results because we use a lot of information, even if it's hidden in the noise. In fact, the fact that you add them, in fact, it's counting. And so basically, the trick in that retrieval step is that we prepare before a large set of simulation, and what we do is that we simulate the atmosphere with a bunch of different conditions of ammonia and temperature and whatever, and from that we define a variance covariance matrix. which is, it's not only the variability of ammonia, it's the variability of everything, and then we perform the retrieval on the whole spectral range, in fact. And so that's, in fact, before performing the retrieval, we have to go through, the simulation allows us to derive lookup tables. So we did separate lookup table for land and sea. In fact, the land is working way better because usually we have a good thermal contrast over land. We don't have a good thermal contrast over sea. And with these values, you have also the error that is coming. So basically, that would be the first try. And then we derived, in fact, a first map that we have to filter. And to filter it, we use the error budget, and we also use the thermal contrast information. And that's providing an improved map like this one, in fact. This is a map, I think, probably, yeah, I don't know, it's only 1 day, I think, this map. And if you do that on a longer period, then you can average and you have a nice map like this. This is a map for, it's an average between the morning and the evening orbit, and from there you can see a lot of signatures. So some due to fires, this is fires, this is fires, so this is agriculture. And if you zoom on different spots, this is fires. You can always associate it with either fire or agriculture or, I don't know the word in English, when you elevate a beast. What's the word? You have several, like pigs and everything. What's the name in English? Yeah, you know what I mean. Okay. So that's also emitting a lot of coals and everything. That's also emitting a lot of ammonia. Okay, and so what we have learned from that is that we have always also to look carefully at what the thermal contrast is, because if you see ammonia, it means that there is ammonia. If you don't see it, it might just mean that you lack thermal contrast, in fact. And that's something to keep in mind when you analyze the data. Just to give you an example, so these are the Landsat picture for, in fact, an irrigation center in Saudi Arabia. As you can see, it was nothing at the early 90s, and then it's growing up. And when you match, in fact, the ammonia retrieval on the Google map, you can see that it's really fitting very well with this irrigation, in fact, in this area. And you can zoom at several spots. This is the Nile Valley, for example. This is the Po Valley. We have, we can see very nice things over there too. And we can do that for several years. So that those are average map over 2008, 9 to 12, with the corresponding error. Okay, and you can also compare that to regional models. So it's working, so this is the work that Martin did, in fact, comparing the IASI observation, this column, for different years, and he compared that to the Lotto Eurus, which is the Dutch model, in fact, for the several years. And you can see that, in general, there's a pretty good agreement. There's still some differences when you look at the intensity of the fires, for example. These are the difference plots. So there's still room for improvement, but in general, it's working pretty well. Okay, I'm switching to another area of the world. So it's exactly the same idea, but now we will look at SO2. There's a place called Norilsk, in fact, which is a place where you don't want to live there, because if you see the area, it's pretty polluted. And it's polluted because they extract heavy metals there. And it's situated further north to the Arctic Circle, and that's a place where, in fact, the thermal contrast in winter is always negative. So that means that we have a good chance to see it, even if it's emitted close to the ground, when we have this negative thermal contrast. So, and that's basically the case. In fact, that's a simulation for the IASI. So the IASI spectrum here is in blue. The calculation without the SO2 is in red. And the difference is here. And basically, it looks like the spectra of SO2, and the noise level is this dashed line, purple dashed line. And so, as you can see, it exceeds the noise level easily when you have a thermal contrast that is negative, and it's the case for this situation. You have here In blue, in fact, the temperature, the vertical temperature, and the surface temperature is here. So there is a difference of 16 degrees, in fact, that allow us to see down to the ground. I should mention, so this place is quite favorable to see SO2 because there's a low concentration of water vapor, and the water vapor spectra really interacts heavily with the SO2. So that's also a good situation to see SO2 because there's a low water vapor content. So do we see it all year round? No, because there's no thermal contrast all year round. So basically, you have here the information from 2009 up to 2012. And as you can see, we see it during the winter months. So that's, in fact, the raw signal from where we extract the SO2. But that's a very large signature as compared to the noise. So from here, several months here again, then every winter you can retrieve, in fact, the SO2. And this is because if you see the correlation with the thermal contrast, here each time we have a very negative thermal contrast, around at least around -10 for each winter. And the rest of the year, it's close to 0, then we didn't see anything, in fact. So it's giving you some idea of how sensitive and that we are not sensitive all the time. But when we are sensitive, it's pretty obvious that it's coming right from noise, in fact, the pollution. Next example, China. So that's a very easy place to look at if you look for pollution. That's on this example, probably you remember it, it was January last year. You saw that in several newspapers, how the visibility was affected and how polluted the area was. So on this picture, if you compare them, you directly see that it's highly polluted on that period. Why was that? Because it's winter, so it's the time where there is a lot of emission due to heating, and also the meteorological situation was that the wind is nearly 0, which is in blue here, and you will see that all this area, in fact, is heavily polluted. On top of that, there is this temperature, inversion of temperature, and that it's blanketed, in fact, the pollution over some cities, in fact. So that's the local observation. It's done from ground-based measurements, and they have this index called DAPI, where they accumulate the concentration of several pollutants. And that index was, in fact, it's saturating because they define, by definition, it cannot go over 500, in fact. So as you can see, for at least 3 cities that are providing here, it's completely saturating for that index. And what we did, in fact, we just looked at the CO observation, and we realized that for some cities, so you have here the same index, that's the ground-based measurements that is available from a Chinese website. So just to do this plot, we had to Google translate the name of the cities, in fact, from Chinese to English. So we did the same observation for CO, and interestingly, as you can see, because the color matches, it's the same cities that are highly polluted. So it's basically in the Beijing area, you have Tianjin and the Hebei province. And so it's not the case from some other cities that are represented here, for example, in green. The 3 in green do not show any increase of pollution from their local measurements, but neither a CO increase with IASI, in fact. So we did some more work on that, and we look at other species. So this is the CO map. It's very nice because you see the cities I just mentioned, they are all in red. And so in the neighborhoods, it's quite clean, but you see this increase of CO very accurately. There's some increase of ammonia. It's not located exactly at the same area, which is quite normal because the ammonia is not emitted by the same source. And SO2 is also higher in this area. And interestingly, that's the first time we saw it. We have also ammonium sulfate that appears in emission, so it emits really near the ground, in fact. So the CO, it's exactly the same story as what I told you for SO2 or ammonia, in fact. When you have this negative thermal contrast, in fact, here it's a simulation. In the simulation, we used different thermal contrasts ranging from -20 Kelvin to +20 Kelvin. And as you can see, the more favorable condition to see an avenging kernel pointing towards the ground, in fact, is when you have this very large negative contrast, and it's followed. So the two peaks here are for minus 15 and minus 20, and the two next one are for plus 15 and plus 20. But as you can see from what I just showed about China, is that it's very easy to see it when you have this negative thermal contrast. By the way, this is the IASI. We use only a single a priori, and you see the retrieval is really able to catch, in fact, this increase of signal because the averaging kernel that is in fact pointing low in the atmosphere. This is interesting too because that's what we call a DOFS, that's providing how much information you have on the vertical. And there's not a direct match because you would have to combine this CO map with the thermal contrast map to see why you see the increase, in fact, in DOFS reaching almost 2, no, I would say 1.8 in this area where it's more closer than 1 outside this area. Yeah, there was another recent event occurring a few weeks ago near Harbin in China. And so we jumped on it and to see, do we see the same? And it's not the case, in fact, because for that event, the thermal contrast is not so good. So we do see an increase of CO in this area, in fact, but it's more the CO that is transported higher in the atmosphere, in fact. So we don't see, like before, a red hotspot everywhere that we can associate it, in fact, to the boundary layer. Okay, and then my last example will be about ozone. So I'll stay, my transition is staying over China just to show you that population density, when you compare it to an ozone map, and that's 0 to 6 kilometers. So I should point out here that ozone in the boundary layer, that's too much to ask, I think, for IASI, because there's ozone everywhere in the troposphere and in the stratosphere. And so just trying to observe 0.6 is quite challenging. But as you can see from here, there is a good correlation, in fact, between the population density and this ozone column, which gives you some hope that you can detect, in fact, the CO providing directly by as a secondary pollutant, in fact. And so this is the work of Sarah, a PhD student working at LATMOS, and what she did is that she compared, in fact, the ozone measured by IASI with the NO2 measured by GOM2. And that's interesting because there are these two instruments fly on the same MetOp platform. And she did that for several years. So that would be the IASI evolution. So the color code is for the different years. And that's 0.8 ozone, and that's the NO2 tropospheric column. And as you can see, the peak of ozone is occurring when the sun comes back in April, where it's the contrary for NO2. The peak, in fact, is during the winter. And you can do that for both hemispheres. And then she did that for several cities. And that's proved to be interesting because she kind of organized the city depending on what she found on ozone. And then she realized that for some cities, she would see like a double peak during the summer. And the first peak, in fact, is corresponding to stratospheric intrusion. So that's the case for Mexico, Los Angeles, and Istanbul. If you look, in fact, at other cities, you will have the peak later in the summer. And that's the anthropogenic contribution, in fact. And here you find the peak again. So you have a double peak on this city and then the single peak on this one. And on those three cities, it's something different that's happening. You have this peak again, and then it's dropping fast, and this is due to the circulation of the Asian monsoon that is, in fact, changing the air mass, and the pollution drops. And she also verified the fact that it's happening later, in fact, in Beijing than in Shanghai or New Delhi, and that's matching well with the IASI data. She did something similar with the NO2. I'm not going to comment on that. And the last thing she's doing now, in fact, is try to use, in fact, this data to try to explain why we see this increase in the Mediterranean area every summer. So if you decide to go for a cruise in the summer, don't go to East Mediterranean area because you will breathe a lot of ozone. And there are really high level of ozone. In the middle of the summer, in the middle of nowhere, you will have high level of ozone. So what she's doing now is like try to use the GOM2 NO2 data for different seasons, together with the CO IASI data and together with the ozone to try to describe why we have this increase of pollution. And what she does, for example, is doing some correlation between all these species to try to understand the things better. And she does the same with the WRF-CAM model. And basically, there are several causes, but they are all combined. It's because it's of course, summer, it's very sunny, usually not a lot of cloud in this area. Plus, the wind is always blowing in the east direction, in fact. So it's bringing the pollutants that are emitted elsewhere towards the east of the Mediterranean area. There are several major cities located in this area, too, that can provide pollution. And last but not least, in fact, this is the PV diagnostic. And as you can see, there is a strong descent of air, in fact, also occurring in the same months in the same area. So everything, all of these factors contribute to the fact that there is a peak of ozone in the Mediterranean area. Okay, so that's basically almost the end of my talk. So can IASI measure everything? No, of course. I only gave you some example of what we saw for pollution, for ozone, and so there are a lot of other examples. I could talk to you all the night, but you won't be happy with that. So the funny thing is that when something happening, everybody is asking, can you see it with IASI? So among this picture, there's obviously something that you cannot see with IASI Fukushima, but I had several phone calls saying, can you see it with IASI? And so they were all very disappointed when I said, no, we can't see radioactive. But for the rest of them, there are some interesting stuff that you always can see from infrared satellites. If I have to say what worked best at what we thought at the start, like 20 years before now, I think we see, of course, much more molecules. I show you some example. We never guessed that we could see very reactive species like, for example, ammonia. We have also formic acid and species like that. At that time, we never understood that thermal contrast stuff. I think we were quite aware of how the averaging kernel works, thanks to the experience with MetOp. We did not really realize how the thermal contrast was important to see things deeper in the atmosphere. At that time, we were also very disconnected from the meteorological community and now we have this MAC project, the whole framework of Copernicus working in Europe, and that brought the two communities much more closer because now, for example, ECMWF is providing forecast by assimilating the IASI data and also the MetOp data, provide forecast of CO, for example. And so these two communities now are really closer, I think. And the fact that we could develop operational application like follow pollution, fires, or SO2 plume is very interesting too. I think what we did not well, in fact, from the start, I think the simulation using models is always difficult because I think the model is smoothing everything, and so some signature that we see now we could never, in fact, predict we would see them because we didn't had enough, in fact, variability in the simulation that we use. I think the coupling for ozone, the coupling with IASI and GOM2 is still quite challenging. There are some tries here and there, but it's still not working in the way we would thought of it. At the start, we also thought we would retrieve things above the cloudy pixel, and that would give you some information on the vertical, but to the best of my knowledge, there's nobody working on that. I think we're still quite weak for climate gas retrieval. These greenhouse gases are still very tricky to retrieve. To some extent, we retrieve CO2 and methane, but it's still not as good as we want. And I think also the assimilation of radiance directly for atmospheric composition purposes still not working properly. What's next? So for IASI, the future is quite bright because we have these two IASI working, and there's the next one scheduled for 2017. Should mention here it's exactly the same IASI because they were built, the three of them at the same time, so it's the same instrument. It will be no surprise. So I'm hoping some surprise will come from the next mission, which is what we call for the moment the IASI new generation. And in fact, it will be an improved IASI. The spectral resolution is a factor of 2 better, which would allow us to have some more information on the vertical. And also the signal to noise is like twice better on average. That should allow us, in fact, to retrieve things with a better accuracy too. And this instrument should fly together with a UV kind of OMI/GOM2 instrument on the future MetOp platform that for the moment they call it MetOp second generation. And they will also have a polarizer instrument like called 3MI, which is the child of the Polder series of instruments. And so it will be like three platforms like this. And the first one is scheduled for launch something like about in 2020. To complement that, we have things in the geo orbit. So we should have what we call MTG Sentinel-4, which also carry an infrared instrument and a UV instrument. But this, for the infrared instrument, is actually a much more coarser spectral resolution than IASI. So to some extent, we could do some stuff on CO and ozone, but I don't expect too much from this mission. But it will be very useful as a complement with the other polar orbited satellites also. So that's just some characteristic of IASI and G. I'll skip that. And so the mission is almost decided. I would say 95%, because we still need the final agreement of EUMETSAT. But so CNES will pay, EUMETSAT will pay, so it's just a final program. And maybe you know that, but in Europe, all the countries have to vote for yes. You cannot say, I don't vote, so they all have to agree they will pay for that. But it's the same story as for IASI, as it's also a meteorological instrument. They are usually keen on paying for meteorological instruments. But this time it will also really be an atmospheric imagery mission from the start. And my last part, so IASI at NCAR, you have the processing of IASI is done with the exact same algorithm as we use for CO. This is from the ACREST website. And we plan to implement also ozone soon. And that's it. I want to thank also the visitor program for inviting me here, because it's always good to take some step beyond and to get rid of all this French meeting and everything where you talk a lot, but then you cannot, your brain is dysfunctioning at the end of the day. So it was good for me to be a bit further away and to think at the whole picture more clearly. Okay, that's it. Thank you.
Thank you very much, Cathy, for a very insightful talk. Do you have any questions?
You mentioned seeing the ammonium sulfate at 1%. Are you able to see any volcanic sulfate?
Yeah, we see sulfuric acid pretty easily, in fact. I think it's in the liquid, because it's appearing a while after the SO2, so in the liquid form, or mix, I don't know. We see it, yeah. For large eruptions, and then for like Kazatoshi, for example, we could track it during months. Like 3 months, we still see some contamination in the northern hemisphere. So it's staying way longer than the SO2, in fact. It's only for the stratospheric eruption, otherwise we don't see it, because it's directly washed out. You know what? One of these Sundays where you have a presentation the next day and that doesn't match well with your family life, then you say, do something for me. Yes?
What is the process of getting methane?
Yeah, so I'm really disappointed about what we have for methane. So I was really hoping we can do much more. I don't know, it's a conjunction of we have, I have several people working with me, and so each of them has like a molecule, and the one in charge of methane did some stuff and then left, and then the things stay like this. So there is also Cyril Crévoisier at LMD who did, I think, nice maps, but he can only do it in the tropics. And I think for methane, you really need the global coverage, because you would like to have methane, see the permafrost stuff and everything. So I think there's, but it's not. I think that if you pay me 3 more people, I think I will improve on the methane product. It's just a question of priorities, I think. But it's hard to see methane. It's like mid-tropospheric methane, I would say. So discriminate what's really useful in terms of sources and everything, it's a bit challenging for methane.
So this might be an interesting project when the Tropospheric instrument goes up.
Yeah.
That simple light precursor, right? Because that's going to measure total column methane.
Yeah. Yeah,
So
that will be helpful. Yeah.
Combination.
Sure. Yeah. Yeah.
You people with species like ammonia, for emission, like in that kind of fuel, you need to know not just the surface temperature, but you need to know pretty accurately the temperature profile in the lower troposphere. Does that information all come from the IASI?
Yeah, that's a very good question. In fact, the information is coming from it's a combined product from different sounders that are on board the same platform. Because the MetOp platform is all meteorological instruments, so there are also microwave instruments like MSU so they derive the combined product with IASI, MSU, and there's 1 or 2 more instruments to have an improved temperature profile. So but that's very true. If we don't have this accurate profile, then we cannot retrieve ammonia.
Is that some kind of limiting in terms of the accuracy of ammonia retrieval? Is that the limiting?
I guess I think the easy stuff with ammonia is the detection. Is there ammonia or not? Not to have an accurate concentration is another story. So I'm guessing if you look at the concentration and you compare that to real data, you might have a factor of 2 difference. That might come also from the temperature profile. But that's why we work more on the detection mode for ammonia. So we do have some concentration, but it's what it is.
So that temperature, does that come from the CMWF analysis?
No, that's one of the products that we have directly from EUMETSAT. It's that they generate these products and they distribute it at the same time as the IASI data. So because we need them in real time too. So that's the issue.
All right. Thanks, Cathy, again.
Thank you.